Hello everyone, and welcome back to another Inch 130 video tutorial. Now in this tutorial we're going to cover the very last concept, which is very nice for you guys, and that is moment of inertia. And it's actually very similar to centroids, where there's going to be two cases, and we have a continuous body, and then we have a composite body. And as you guys can guess from centroids, the continuous body is going to require us to use integration, while the composite body is a little bit nicer and we can use special relationships, which we'll discuss later. So this video will be moment of inertia for a continuous body. And the formula is kind of funny because it might scare you guys because it looks a little bit more complex than the centroid formula for integration, but it's actually a little bit easier because there's certain tricks that we do for moments of inertia that makes things really easy. But I know one of the first questions a lot of you probably have right now has nothing to do with the calculation of it. It's rather, what is moment of inertia? So before we begin the example, I'm also going to explain kind of what is moment of inertia and how do we actually use moment of inertia in real life design. So as you guys will see, it's actually a very important parameter. So I think with that being said, let's jump into the video. Alrighty, so looking at this example, what I would like us to do is determine the moment of inertia of the shaded area about the x-axis. So real quick, I'm just going to highlight the x-axis because that's going to be very important. So we're going to take it about this x-axis. So again, like I said, before I begin, it's very important to just talk about what is moment of inertia, just so you guys have a general understanding of why we're doing this. Why are we calculating this? Because for friction, it's pretty obvious. Friction, well, that's real life examples. Trusses, well, you guys have seen truss bridges. You guys guess why we do that. And the same thing goes for moment in shear, because again, beams are everywhere. You guys see this. But what exactly is moment of inertia? So what it is, it's basically a parameter that defines how easily an object bends. Oh, Clayton, why is that important? Well, if we have a beam, so I'm just going to draw a simple beam right here. I'll do it right here. Why not? So if I draw a simple beam like this, and we have just simple boundary conditions like this. And real life loads, they're usually distributed across the beam. So we're going to have, let's say, a distributed load that comes across the beam like this. So excuse me while I draw this. I know it's going to be super annoying for a lot of you guys who just want to get right into calculations, but it's very important to understand why are we doing this. So you guys know that what we're doing, it's not just for fun. It actually has something to do. So of course I'm just going to define a couple things real quick. So this will be a load, which we'll just say is W. And of course the beam also has a length, which we'll call L right here. So although it's not dealt with in this course because we're assuming rigid bodies, so no deflections, what happens to this beam under load, as you guys may have guessed, is it's going to deflect. It's going to have a nice deflected shape like this. And as engineers, we're worried about one thing, and that is the deflection of this beam at the midspan right here, which we call delta. And when we're designing buildings, this deflection is very important because when we design things, we actually consider two things. The first one, as you guys may have guessed, is strength. So we obviously don't want a building to collapse or to fall. So the first thing that we do when we design a building, we make sure that the beams are strong enough to carry the loads. That's pretty obvious. But the second thing we check for is what we call serviceability, and that is to make sure that the deflections in all the beams are really small. And what that really means is, let's say we have a really long beam. It can actually be fine for strength. It can support all the load that we want. But let's say that it deflects 30 centimeters. So our whole beam will have this giant arch in it, and people walking across won't feel very safe. The best example are those suspension bridges, the ones just for people that they have in the mountains, stuff like that. Everyone gets really scared when they start walking on it because it starts swaying and deflecting, and well, we don't want that. If you guys are going down the bridge here in Edmonton and the bridge started going down as your car went on it, things would be pretty scary. So we also designed to make sure that the deflections aren't large. And if we want to find this deflection of the beam, assuming it's elastic, so for those of you who talk about concrete and stuff like that, I'm not referring to concrete, just nice elastic structure. This delta can be found with the following formula. So delta is equal to 5 over 384. So this is just the constant out in front. And then the parameters are WL to the 4. So those parameters are just the load as well as the length, and that makes sense because if the load is high, well, we're going to have more deflection, or if the length increases, again, we're going to have more deflection. But then at the bottom, we have a special term, which is E and I. And I'm just going to put this over here. So what we call this EI, we call this the stiffness of a beam. So stiffness is comprised of two things. So I'll just put another arrow. So it's comprised of E, and it's also comprised of I. So first off, we're thinking about stiffness of a beam, how strong something is. It's a combination of actually two factors. The first is what material is it made out of. For example, a steel beam is going to deflect a lot less than a plastic beam. It's stronger. So E is a material property. It's based on the material. So again, for steel, it'd be different. For steel, it's 200,000. For concrete, it gets iffy, but I don't know, maybe 18,000, so a lot less. And each material has a different E value. And the second one, this I, this is the moment of inertia. So this is why it's so important. Moment of inertia. Oops, just about spelt inertia wrong. So moment of inertia. And what this is based off of is a body's shape, so the geometry of a cross-section. And it makes sense because certain shapes, as you guys know, are easier to bend than other ones. So this is why we have the I factor. So if we look at the end of this course, you guys, if we were to look at this formula, we now know W and L. E, we don't know, but this is actually next year in a class called Civi 270. You guys will discuss this one a lot, but it's actually very easy in design. Don't let them scare you. It's actually for steel, 200,000. Nice and simple. So the only thing that we still need to know is this I factor right here, which we're covering this week, which is moment of inertia. So looking at this question, this is what's going to be very important to you guys. Moment of inertia is going to change depending which axis we want to take it about. That's why it's very important in your question, in your finals, in your labs, in your assignments to find out what axis they want the moment of inertia about. And in this question, it says very clearly we're looking for the moment of inertia about that x-axis. So we come down here. Well, actually, another step we should do is we have to kind of figure out, but this one's more simple. We have to ask ourselves, is this a continuous body or is this a composite body? And if we look at this, well, it's a mathematical curve. It's definitely going to be a continuous body. Alrighty, so when we're dealing with moment of inertia, we have two formulas that we're going to have to remember. And these are both on our formula sheet, but they're actually pretty easy to remember. So the first is Ix is equal to, and it's going to be the integral of y squiggle squared times dA. So this formula actually looks very similar to a centroid. The one thing that you're going to have to always remember, though, is the squiggle in these formulas is always squared. And what I mean by that is if we look at Iy, we see that this is going to be the integral of x squiggle squared times dA. So we're always going to have to remember that squared when we take into account these formulas. But as I mentioned, it's very important we figure out what axis we're taking the moment of inertia about. So if we look at this one, we're dealing with the x-axis. So what that tells us in our formula sheet is we're going to go to this formula right here. And at first it could be a little bit scary because it has a squared, it's an integral. You guys might not like it. However, if we look at this formula, it's actually only comprised of two things. Y squiggle is equal to question mark, and dA is equal to question mark. So the question becomes, how do we determine these two values? And it's actually the exact same as centroids where we have to take a slice. So if we come up here, what I'm going to do is I'm just going to copy this real quick and move it down here. Put it down here, right here. Perfect. I'm just going to erase this x-axis because we don't need it. And another thing I'm going to do to fill in real quick is we actually know what A and B are. So A is 4 and B is 2. So right here, we know that A is 4 meters, just to make this a little bit clearer. And B is equal to 2 meters. And our equation here is kind of hard to see. So what I'm going to do, it's y over b, so it's going to be y divided by 2 is going to be equal to x divided by a, so x over 4 cubed. So what I'm going to do real quick just to make this convenient is actually just solve for what x is. So if we move everything to the other side, what we're going to do is x is going to be equal to 4 times y over 2 to the exponent 1/3. So this will come into play later, as you guys will see. But remember, our main focus right now is finding out two things. And I'll change the color. What is y squiggle and what is dA? So normally what we would do to find these values is we take a slice. And that's exactly what we're going to do this time. We're going to take a slice. But remember last time we encountered kind of a funny situation where we can take a horizontal or we can take a vertical slice. And both of these will give us the same answer in the end, but one of the integration would be a little bit easier. And as you guys will see, the exact same is true for moment of inertia. However, I'm going to tell you guys not what I would call a little trick, but this is what I like to do, and it usually makes things easier. Very rare cases where it doesn't, but usually does, so this is what I like to stick with. And that is this. If I'm finding Ix, oops, I'm still in the highlighter. If I'm finding Ix, what I want to do is I want to take a horizontal slice. So again, you can take a vertical slice, it'll still work. This is just my preference for moment of inertia. If I'm looking for Iy, I want to take a vertical slice. And the reasons for these will become apparent in these formulas. And actually, I can show you guys right now. So if we look at Ix, we have a y squiggle right there, a y squiggle, which is going to be a function of y. And if we take a horizontal slice, what that does is give us a dy. So what will happen, and the same goes for Iy, it'll give us a dx, and this will work with the x squiggle, is it'll just make the integration a little bit easier. And I'll show you guys that as we go through. So if I'm dealing with Ix, which is what I'm doing, I'm going to take a nice horizontal slice. So let's just go take a slice, let's say this, right here. So here's my slice. So remember, to find dA, we're going to need the volume of the slice. So if we took a horizontal slice, we know that this is going to be dy. Now the question becomes, okay, what is the length of this bar? Well, we know that the distance from the axis to the end right here is 4 meters. So this is going to be 4. And then we know the distance from here to the slice, well, that's just going to be x. So therefore, this length right here is just going to be 4 minus x. So not too bad. And from there we can go dA. So remember, dA is just the area of the slice. Is going to be equal to 4 minus x times dy. So that's not too bad. So far, picking a horizontal slice hasn't really helped us. If anything, it's actually kind of kicked us in the butt a bit because we have a 4 minus x instead of just an x or just a y. But this is why I like to pick it right here. It's because we take a horizontal slice and we have our centroid right in the center. The distance to the centroid, oops, I zoomed in a bit. The distance to that centroid is actually just going to be y. So y squiggle is just going to be equal to y. And I'll put that right here. Y squiggle is equal to y. So now when I sub everything into our formula, Ix is going to be the integral of y squiggle squared. But now we know that y squiggle squared is just y. So this can be y squared. And then we're going to have 4 minus x times dy. And now this should be apparent why I wanted to pick a horizontal slice, because this y squiggle is already going to be integrated with respect to y. I won't have to mess around with y squiggle at all. It makes it really, really nice and easy. But now we have two problems, just like we would in centroids. First one is, actually I'll write these down so you guys know exactly what they are. So problem number 1, limits. We need to know what we're integrating through, which are boundaries of our curve. And the second one is we have an x times dy. We can't integrate x with respect to dy. But what's nice is we have a nice formula here to change our x into a function of y. So we're going to substitute this in and then find our limits. So for the limits real quick, if we have a dy, oops, I just about erased it. Since we're integrating with respect to dy, our hint is we're integrating over this y-axis. And we know that our curve goes from 0 to 2. So this integral actually becomes ix is going to be equal to the integral from 0 to 2 y squared. And we're going to have 4 minus, and then we have to substitute our formula up here for x. So it's going to be 4 minus 4. Oops, my brackets aren't that nice tonight. 4 minus y over 2 to the 1/3 times dy. So now if we look at this integral, we have our limits defined, and our whole function is in terms of y, and we're integrating with respect to y. So everything is good to do, good to go. Good to do. That's a word I've never heard before. So the next part is calculator. So again, please just throw these in your calculator. It'll make your life a lot easier. So once we throw it in our calculator, what we get is ix is equal to 1.07 meters to the 4. Highlight this because this is my answer, and that's it. So moment of inertia, oops, if I can draw the box right. So moment of inertia, as you guys see, not that bad. Oh my gosh, this is, okay, never mind. Moment of inertia is not that bad. My drawing skills, those are questionable. So this is our final answer. We're now good to go. And that's the question. So moment of inertia sounds really scary. It's actually not that bad. All you have to do is find out which formula you want, and all you have to do to figure that out is decide what axis the question asks. The question should be very specific in telling you what axis they want the moment of inertia about. So that concludes this question. Thank you guys all so much for listening, and I'll see you guys in the next example where we cover moments of inertia for composite bodies. Thank you so much, guys. Have a great night.